All right, so in this particular thing, we're going to go over the 2019 number 4, and I'm going to make a video solution guide for you. And then this one, it says, tumbleweed commonly found in the western United States is the dry structure of certain plants that are blown by the wind. Cochea, a type of plant that turns into tumbleweed at the end of the summer, is a problem for farmers because it takes nutrients away from soil that would otherwise go to more beneficial plants. Scientists are concerned that cochea plants are becoming resistant to the most commonly used herbicide called glyphosate. In 2014, 19.7% of 61 randomly selected cochea plants were resistant to glyphosate. In 2017, 38.5% of 52 randomly selected cochea plants were resistant to glyphosate. Do the data provide convincing statistical evidence at the 5% level of significance that there has been an increase in the proportion of all cochea plants that are resistant to glyphosate? So before we start this problem, we need to know what we're talking about. And when we go through here, the key thing I know that I'm going to do is I'm going to do some kind of test. And I know I need to do a test because it says, do the data provide convincing statistical evidence? That means do a test. So when I go to my tests, I need to see what do I have. Do I have means or proportions? Well, I see all of the percentages here, so that means I have proportions. And I have two sets of proportions because I'm looking at two different years. I'm looking at the year 2014, and I'm also looking at the year 2017. And what I want to know is, has the proportion increased? So has the proportion increased? So I'm going to do a hypothesis test where I use fats. And what we say is, let's define the P first. So our P here for 2014, we'll call that P of A, is equal to the true proportion of cochea plants in the year 2014. P of B is equal to the true proportion of cochea plants during the year 2017. And what we're actually interested in, we want to know, anytime you look at two samples, you always look at their difference. So we want to actually find the difference, which we're going to call P. I'm going to make it P, and I'm going to define it as this. I want the larger difference to come first, or the larger value to come first, and that'll be P of B here. And I want to subtract off P of A. So this is the value that we're defining as our parameter now, and this is equal to the true difference. This is the true difference in proportions between P of A and P of B. So we have the parameter defined. Now we need to come up with our hypothesis. Well, our hypothesis here, anytime you do a two-sample test, will always be some kind of difference is equal to 0. So we want to do our null, H naught. And remember, we define this value P, so we're interested in now, P. P is equal to 0. There is no difference between P of A and P of B, so they haven't changed over the years. Versus the alternative, HA, is that we want to know now, has there been an increase? So we want to know if there's been an increase. That means HA is going to be that, well, if we wanted to increase, I want P of A, or in this case, P of B came first. P of B has to be greater than P of A. An equivalent way to write this is to say P of A, or P of B, minus, looking at the difference again, P of A. And remember, I got this. If I'm doing this, I'm subtracting up this P of A from this side, moving it over here. When I do that, that is going to be greater than 0. So this is the way we want to write this with this equivalent expression. All right? Or we can write it, because we're defining this right here, we can write this as just P greater than 0. We can write it like that, P greater than 0. Now, we need to do our assumptions. So the assumptions here, the first one is that the sample is random. And if we go up and look at this problem, it tells us that both of these years they selected randomly selected cochlear plants. So when we look at this then, we know that the assumption of being random is already stated. So this is stated. The second assumption is we need to show success failure. And what that means is that N1 PA has to be greater than or equal to 10. N1 QA has to be greater than or equal to 10. Also, N2 PB has to be greater than or equal to 10. And N2 QB has to be greater than or equal to 10. When we go here and we look at it, our percentages for each one was given. And we have 38.5% of, 19.7% of 61. So if we do that math in our calculator, 0.197 times 61, I get 12.017. So for the first one, to meet this, I did 0.197 times 61. That is greater than or equal to 10, so that's 12 greater than or equal to 10. And I'm going to do the remaining, which will be 1 minus 0.197, that's 0.803. So 0.803 times 61, that's greater than or equal to 48, basically 49. We'll just call it rounded off, 49. So that'll give you 69. And then we need to do the other one, which in that particular case, it was 38.5%. So we're going to do 0.385 times, and they only had 52 in that sample. That's equal to 20.02. So we'll just say 20. And then we'll do 1 minus that 0.385. Then we get 0.615 there. We'll multiply that by 52. And I get 32 for that one. So these are your values. They're all greater than 10, so we meet that condition. And then the last part is to do our independence condition. Now remember, we're showing independence in general just because we want to make sure that we're not sampling too much of the population, because we want those probabilities to remain the same. And so here's what the independence is going to say. Remember, we say it like this: surely. Let's look at the respective things. We looked at 61 in 2014, surely 61, and we looked at 52 in 2017. Surely 61 and 52 cochlear plants are less than, remember, 10% of all cochlear plants. And the other thing we have to say is that the samples are independent of each other as well. Because you can't be in both 2014 and 2017. So we have to make two independent statements when we have two samples. But now that we have that, we can actually go and run the test, right? And again, for this particular test, we're going to use the calculator. And when I do that for this particular test, I get these values here. I went to my calculator, and notice how I set this up. I'm going to do a 2 proportion Z test, And this should be menu 676, 2 proportion Z test. And in this, I'm going to set up where I notice my successes for X1. That is the number of successes I had in my first population. But when I wrote it, I wrote P of B first. So that's my first population. And the number of successes in P of B was 20. We calculated that here in our success failure rule. Out of the total sample, which was 52, and then the second sample had 12 successes out of 61. And so when I look at this now, calculating that, and I ran the test, and notice the name of the test is given here, 2 proportion Z test. So I'm going to write this as a 2 proportion Z test, a 2 prop Z test. And I'm going to use this Z value right here. I'm going to write the probability that Z, remember, we take on whatever the sign is of the alternative. In this case, our alternative is here is greater than. So the probability that Z is greater than the actual Z value, is 2.21. That's equal to your P value right here. 0.014. And so from here, once we have all this information, we can go ahead and make a decision now. Remember, your alpha value, the significance level, was set up here in the problem at 5%. So if alpha is equal to 5%, if alpha equals 0.05, I want to compare the p-value first, 0.014. That is less than 0.05. Remember, if the p-value is less than alpha, we will reject HO. We're going to reject the null. Why are you rejecting the null? Well, there is sufficient evidence or enough evidence here to support the alternative. And the alternative here, remember what your alternative was? Your alternative was that there was an increase. So we actually want to write that out. There is sufficient evidence to support that there is an increase in the proportion of cochlear plants.